Okay, very good. So I guess, yeah, I guess we can get started. As I mentioned, next class on Tuesday will be at the same time, but it will be online. So that's the only difference. Other than that, let's go back to harmonic functions. And so let's see that for a group, again, so we start with G, let's say a countable group. For now on, mu, a measure, probability measure on G. And we recall that f as a function from G to R is harmonic, is mu harmonic, is harmonic in this discrete sense, if f of G is the average of where the average is taken with respect to this measure mu of the function computed at GH. So again, the way to think about it is in the Cayley graph of this group, you have G, and then H is the increment, and then GH is a neighbor node, even though this does not have any graph in it, but you can think of it like that. Okay, so this is true. So it's the average of the neighbor nodes with the, and this mu tells us how to do the averaging. But again, you could have more complicated situations. Again, the support of mu could be infinite. So the corresponding graph would have infinite valence if you want. So it could be different. Okay, and also in terms of notation, we have H infinity, G mu, which are the bounded harmonic functions, f from G to R bounded and mu harmonic. And then we have the positive function H plus of G mu, which is f from G to R, which is positive and mu harmonic. So the constant functions are in this space. The constant positive functions are in this space as well. Well, sometimes there are more things. But we haven't seen any new things yet. So let's see. So here's a nice example. An example of a bounded non-constant harmonic function on a tree. And so we discussed it very briefly. I started, setting it up, and as a sort of a question. So we discussed a little bit some things, but let's see. So consider, of course, a tree is a Cayley graph of a free group. So you can also think of it as constructing a harmonic function on a free group. So consider a Q plus 1 regular tree. Let's call it TQ. Maybe TQ plus 1. Okay. So in our example, Q will be 3. So we just get it for a regular tree. Right. And the simple random walk on it. So meaning that you're taking the walk which has uniform on its neighbors. So we just take the measure which is uniform on the neighbors. So, right. So in terms of similar, okay, for in terms of groups, similarly, right. So you can take F. Yeah, you can take also, you can take G to be free group on K generators, where of course 2 times K is Q plus 1. Same thing. And where mu is, the unit for measure, so 1 over 2K sum of AI plus sum of AI minus 1 equals 1 delta. So we're taking the measure on the standard generator. Okay, so here's the picture. So let's draw it like that. Okay, we have this tree structure. Something like this. Okay, so we pick a reference point, let's say here. Say this is our origin. And we want to, the idea is it's somewhat not so hard to construct a function which is harmonic, say on the right-hand side of this. And we saw last time what is the trick. The trick is, okay, we define the function to be 1 at the origin, and then we go down exponentially at each step. Right. So this one would be q to the minus 1, q to the minus 1, and this one would be q to the minus 2, q to the minus 2, q to the minus 2, and so forth. So this will be q to the minus 2, and so forth. So the first claim is this function is harmonic on the right-hand side. So for every node that is to the right of this bisector, then we get the harmonic condition. So let's see. So the first claim is that f of x, which is just q to the minus the distance between O and x, is harmonic on where? On the right-hand side. So what's a way to say the right-hand side is, well, we can give a name to this point. Let's call it y. And so we say that, so if you look from the origin, if you look at the geodesics from the origin, this covers all the geodesics from the origin, except from the geodesics that go through y, because those are on the left. So this is usually called, so this is tq plus 1 minus this is called the shadow or the cylinder set. So the cylinder set of y, where in general we can call C of y is all the nodes in the tree such that the geodesic from here, this is a tree, so it's simple. Every geodesic sort of, just tracks some other geodesic. So O to, the geodesic from O to Z contains y. So this is usually called the cylinder set. So okay, that's fine. Now, clearly, if similarly we forget about the right-hand side and we only look at the left-hand side, well, we also have a harmonic function. We know what it is. And it's easy because, again, you have 1 here. You can have q to the minus 1 here, q to the minus 1, q to the minus 1 here, q to the minus 2, q to the minus 2, and so forth. Oh, that's fine. So similarly, okay, so this claim is clear, right? So sure, maybe the computation is already done the computation. Now, the second claim is similarly. Yeah, if you do f of x equals q to the minus the distance between x and y, where y is at the particular point there, is harmonic on the tree minus, and then in this case the left-hand side. Yeah, so the left-hand side is indeed the whole. Is the cellular set of y. That's the easiest way. I can also write that as a cylinder set, but then you have to change the center of it. So it's okay. That's fine. Of course, the other thing is that if we allow this to be negative, so we take the distance with sign. So we go like 1 q squared q cubed. This is still harmonic, but the problem is that it would not be bounded, right? So both of them are bounded. But of course, there is a problem because the center nodes. So if we test the condition in the center nodes, the other condition fails. Right? So how do we fix it? And does anybody know how to fix it? So the trick is that not just this function is harmonic, but we know that the space of harmonic function is, what kind of algebraic structure is it? It's a vector space. Very good. And we know two harmonic functions. We know this one and the constant. So it's not just true that this is harmonic, but we can have a, some constant, plus b times this. So for any a and b in R would also be harmonic on this side. Because it's a linear combination of harmonic functions. And so it means that here, instead of this function, we can bring more, you can put everywhere, you can put a plus b q inverse, a plus b q inverse, a plus b q inverse. This is a plus b times 1. This would be harmonic. And now you start seeing why is this good. Why is this good? Because now we have two nodes to control, for which the condition potentially still fails. We don't know. But we have 2 degrees of freedom because we have a and b, these two parameters. So now we can fix these parameters, set them so that the condition, the harmonic condition, also holds on 0 and on y. So this is claim 2, and this is claim 3. Again, this is a feature of the fact this is a tree. It makes it simple because really there's only one edge along which we have to control, right? There's no other strange loop because otherwise maybe there's some other loop. So if you do something one way, you get it the other way and so forth. So it could be a bit trickier. What if I don't see the chat? Okay. Okay. So yeah. So in order, so we need to find. We hope to find A and B such that harmonic condition holds at 0 and y. Okay. So at 0 or O, you see the value that we already know is 1. And you see, what would the value be if we apply the formula on the left? Well, you see, this is a plus b times 1, a plus b times q to the minus 1. So this would be a plus b times q. Right? So if you apply the same formula, this would be a plus b times q. So the first formula would be that 1 has to be a plus b q. So this is the value at 0. And for the value at y, well, we know we are given the value of a plus b from the left formula. And what would the right formula tell you? What? No. So let's see. This is 1. This is q inverse. What's next? Right, so this is q to the minus 2, q to the minus 1, q to the 0. This would be q. That's right. Yeah. Because in the orange function, you know, yeah, on this central line, you would have the powers of q. But this is very closely related to a Horo function, if you know what that is. So okay, so this would be q. So this is the elementary middle school problem. Now, hopefully we can still do it. So hopefully it's written correctly. That's the most important. Yeah, I think it is. Yeah. Okay. So, okay. So now A is, on the one hand, is q minus b. On the other hand, is 1 minus bq. So b times q minus 1 is 1 minus q. So b, so of course q is different from 1. Otherwise, this construction doesn't work. So, right. So b is negative 1. And then a, well, a is q minus b, so a is q plus 1. Okay. So now we are done, basically. And so we can write the formula. So in the end, f of x has to be of the following form. So this is q to the minus, let's say, the distance from O to x for, again, for x in the tree minus the cylinder set of y. So basically on the right-hand side of the tree. And then on the left-hand side of the tree, you have q plus 1 minus q to the minus, okay, to be sure, let's rewrite this precisely, right? Yeah. So what is the value here, for instance? Right. So the value here would be q plus 1. So it has to be, yeah, q plus 1 minus 1, because it has to be q. And this one, then the next one has to be q plus 1 minus q to the minus 1, and so forth. So this is q plus 1 minus q to the minus 2. Okay. So what is the exact formula is q to the minus the distance between O to X. No, this is to minus 1. See, that's the issue. Plus 1. For instance, if you're at Y, the distance is 1. So this is 0. So q plus 1 minus 1 is q. So this is for X. And again, here, yeah, it's always like that. Always like that. So this is q plus 1 minus q to the minus 2 here, and so forth. That makes sense? Yes?
When we say the right-hand side is that function is harmonic,
Mhm.
we're talking about we're restricting the measure to the subgraph.
Right. So what's a harmonic is a local condition, right? It means that the function is the average of the function on its neighborhoods.
Right. So specifically when we're looking at neighborhoods of the origin.
Yes. Right. Yeah. So right. Yeah. So here you're saying. Yeah. So here I did not. Yeah. When I said this, I did not want to include the origin in this computation. Yeah.
Okay.
Yeah. Because we don't know. Yeah. So this was a boundary. Yeah. This was a graph becomes. Yeah. If you technically this becomes a graph with boundary, this becomes boundary node. So you don't need to check that. But yeah, that's what I meant in this discussion. But yeah, you could say this is harmonic. Also, yeah, you can also remove 0 if you want maybe to be super precise or to not be confused. You could say that this, will remove 0 here.
And then we adjust the two boundary points to make it.
Yeah, exactly. So this is maybe, just to be super precise, maybe let's just remove that. So then, yeah, so basically I didn't want to check here. Yeah. More questions? Yeah.
You said like the left hand side like with B1 multiply some Q and the right hand side is B2. Can you like make the adding by constant to be like multiplied by different constant on both sides and then match condition? So like you saw one side is like all B1 times Q and the right hand side is B2 times Q. And then like you match the condition to the origin.
Well, but you need to play with the constants as well, right? I mean, this function cannot go to 0 on both sides, right? I mean, this function goes to 0 on this side, goes to q plus 1 on this side.
Oh, so you can now have it goes to 0 on both sides.
No.
Oh. So it must be like adding some constant. So
Yeah. I mean, in fact, what it turns out is for every boundary point on the tree, you can construct such a function and go to 0 towards that boundary point. So of course there are many other harmonic functions, but you do need to do this non-trivial linear combination to match them up. You cannot just multiply everything on the left and everything on the right. Yeah. More questions? Okay, good. So I don't know. So this is a nice function that is somewhat surprising. You've never seen it, but it's very explicit. So you can draw very explicitly a function once you keep track of this geometry. Okay, so this is to show that indeed whenever there is a group that is not abelian, then the situation becomes more complicated. In fact, so this shows, so as a corollary, as a corollary, we see that the space of bounded harmonic functions for the free group, for instance, for the standard generated set, is not just the constant. So its corollary is if mu is indeed standard measure on free group generated by the AI, then the space of bounded harmonic functions is bigger than just R. And in fact, you can prove, so exercise which comes very closely related to what I said before is the dimension of the space over R is infinite. And basically the idea is that for every boundary point of the tree, you can construct a similar function. So already you will start seeing the relation between the space of harmonic function and the boundary behavior of your group. Okay, so now let's go back to abelian groups actually though. So we still want to say a few things on this type of groups, not just abelian, but other groups that have some flat structure, something like that. So we proved before that the space of harmonic functions on Z with the, so we already, so recall the following, that we proved that if mu is just simple random walk on Z, then the space of bounded harmonic functions on there is just trivial. Now, what about it in higher dimensions? So there are two ways to show the same is true for abelian groups. So in fact, the space of H infinity of ZD mu is trivial for any measure mu, let's say, that generates ZD such that the semigroup generated by the support of mu, so put the plus to say the semigroup is ZD for every D. So this is a theorem of Chauquet-Denis. So we won't see the complete proof of this, but we will see two different proofs. At least that the simple random walk in ZD in Z2 has no harmonic function. So let me first state proposition. So suppose let G mu be a measure group such that the random walk corresponding driven by mu, the corresponding random walk is recurrent. For instance, this is the case. For instance, it's the case for random walk in Z2 with, but then for higher D, this is not only the case, but let's observe the following. Then, yeah, indeed, H infinity of G mu is only the constant. Okay. So let's look at the proof of this. So this is probabilistic proof. So remember last time that when we wanted to construct this harmonic function, the harmonic extension, so we had this finite graph with boundary. And then we said, okay, I start somewhere, I run the walk, and I stop when I hit the boundary. And this is an example of a harmonic function. So that's how you would do the harmonic extension using random walks. But now here, if the random walk is recurrent, we can do something similar. So consider, okay, so we start with f, which is a harmonic function, bounded. And then take f of Wn. So Wn is a random walk on this group. And again, so if we look at f of Wn as a random variable, this is also a martingale. We basically already saw this proof. Because of the harmonicity of f, it means that f is on average constant. So you're choosing your destiny randomly, but since f is harmonic on average, your destiny will be fair. Your average value of tomorrow will be the same as the value of today. So then this is a martingale. And it's bounded. Hence, there is a limit. Hence, what we can construct a function that there is a limit. So the limit of f Wn exists almost surely. But then we want to use the fact that this is a recurrent walk. So again, we pick 2 points. We pick E, and we pick another element G. And so the walk will visit almost surely E infinitely often, and almost surely G infinitely often, right? So since random walk is recurrent, then almost surely there exists, two sequences W and K. Say the sequences NK and MK, such that f of W and K equals f of E, and f of W MK equals f of G for every K. But then the limit exists. So if the limit exists, it means that these two values have to be the same. Since the limit exists, then we have f of E equals f of G. So this is true, right? What do we need from G? So G has to be in the semigroup, so generated by the support of G, so that there is a positive probability path from E to G. If there is one, then the walk is recurrent. So once you get once to G, you will recur to G. Okay. So for every G in the semigroup generated by the support. Okay. And so we assume that that is the case, I guess. And so we assume that that is the same as the whole group. So F is constant. Okay. So that's one way to show that the boundary is trivial. If the random walk is recurrent, then the boundary is trivial. Of course, for Z2, this is enough, but for Z3, of course, this is not enough. Okay, so now let's look at another proof. Let's see. Let's see if I remember correctly. Let's see. I think this proof should work in this following generality. So let G be an abelian group. Okay, and mu. Okay, so mu a symmetric measure. G meaning that mu of G equals mu of G inverse for every G. And okay, again, with the support generated by mu, in this case, since it's symmetric, it's the same as the support for the group, and the semigroup are the same. Okay, and okay, and for this proof to work, for at least in a simple case, we need the finite support. So let's see, and let me symmetric finitely supported right here. Okay. So then I want to say that H infinity R mu is just yeah. In the notes I wrote it for ZD, but I think this proof should work. Let's let's check. Okay, so what do we need here? Well, first of all, we need again just a little bit of functional analysis to say what is the shape of the space of harmonic functions. So before writing the proof, we look at minor. Yes, so we want to say something about closed convex subsets. Sets in topological vector spaces. Just a minor detour. So, okay, we have following definition. We say that if K in topological vector space V is a subset of a topological vector space V, then the closed convex hull of K, well, is the smallest closed convex set that contains K. And in this case, yeah, maybe not empty. Yeah, the closed convex hull of K is the intersection of all closed convex sets. Containing K. Okay. The other definition is that the point in K is extremal, of course. Point Z in K is extremal if it cannot be written as a convex combination of two other points. If whenever Z can be written as AX plus 1 minus AY with XY in K and A in 0, 1. That either Z equals X or Z equals 1. Yeah, I guess this, I think if we say it like this, we have the case where X equals Y, it's still fine. I mean, it's just like, right. Or you could say X is different from Y. I think that would force alpha to be H be 0 or 1. But if X equals Y, it could be anything, but it's still fine. Okay. Anyways, you don't want to write it as you know. Usually you have X and Y, and Z would be a point in the segment, and we don't want to write that. And now we have famous functional analysis theorem that talks about extremal points in a convex closed set in a local in a topological vector space. So what is the theorem? So the famous theorem is the Klein-Milman theorem. Is that if K is a compact non-empty convex subset of a locally convex topological vector space, Right? So for instance, a vector space whose topology is given by semi-norms, but in general, well, it could be normed one easier. So then K is the closed convex hull of its extremal points. So of course, yeah, of course, this is somewhat simple to think about it in Rn, right? It's like you have a shape, have a convex shape, and you have extremal points that they're finite if you get polygon. It could be infinitely many, like if you have a circle, but still everything inside, every point inside is in a closed convex hull. In fact, it doesn't say immediately this is a linear combination because I think it's a higher dimension. In infinitely many dimension, it just says it's a closed convex hull. So it's going to rather more implicit. Right here, of course, you could have, I don't know, convex combination of 3 points, you get this. So what's the upshot of this is that if you want to show that some space is trivial, for instance, you want to show space is a point, and it's convex and closed, compact, then it's enough to show that it has only one extremal point. That's the usual trick. Like a similar thing, you want to show that there is only one invariant measure. We sometimes just prove that there's one ergodic invariant measure because the ergodic measures are the extremal points in the space of invariant measures. Okay. Right. Yeah, in fact, okay, I can write this example even though it's not directly related to the application that we have. Indeed, if you have x mu x a mu t is measure preserving system, you can say that k is the simplex of invariant measures. So this is a, oh, sorry, xa, no, sorry. We don't have a measure yet, sorry. So if P from xa itself is measurable, then we take all the measures that are invariant by T. And this is indeed is compact if the space is compact, but it's definitely the closed convex. And the extremal points of K are precisely the ergodic measures. So that's another natural application in dynamics. But here, actually, now we're not going to look at the measures. We're looking at the harmonic function. Okay, so in general, so here what we do is if again if we start with G mu a measure group, and let's take mu finitely supported. And the group subgroup generated by the support of mu is G. Then we can look at a positive harmonic function, H prime plus G mu. These are positive harmonic functions, and in fact, yeah, we want some normalization as well. So actually, yeah, let's write like this. So F from G to R positive harmonic. No harmonic first. And then let's normalize such that F of 0 equals 1. F of identity equals 1. Yeah, just by rescaling, we can normalize it like that. Because you know, by the maximum principle, if there is a minimum, the minimum has to be cannot be inside. Because you know, if F is 0, then this would be minimum of this function. And then this would imply that a function is 0 all the time. Okay. So recall note, by maximum principle, if F of E is 0 and F of G is non-negative for every G in G, then F has to be 0. Okay. So, okay, so this H plus is convex. This is clear. Because if you take convex combination of positive functions, it's positive. F of the identity is 1. And the harmonicity condition is linear. Okay. It's non-empty. Because the function 1, constant 1, is in this set. Now the issue is the compactness. Okay. So to show the compactness, we need some a priori bounds, so to speak, of this function. But the a priori bounds are not so complicated. So H plus is compact. And that's where we use the finite support. I think. Yeah, I don't know what the proof does in general, but that's. I don't know if it's still using this fact or not in general. But for this one, let's do it like this. So we need some a priori bound on this function to say that this family of functions is compact. Okay, so what are the a priori bounds? So well, you know that by harmonicity, you have that F of G is the sum. So you can take the n-step distribution. You do mu n, the nth convolution of h, f of gh is still true. Right? And in particular, if we take, right, so in particular, f of g is less or equal because, bigger or equal than this one, because this is the sum of positive terms. And if mu and h is positive, and you set g equals e, well, you have that f of h bounded above by f of e divided by mu n of h. Right? So in general, so every h, you see, the support of mu generates G as a semi-group. So for any h, there exists some n such that mu n h is positive, right? And so we set C of h to be 1 over mu n of h. We pick some of them. Some. Okay. And in fact, f of identity, we normalize it, so it's 1. Okay. So what do we see? We see that h plus g mu is contained in this product from 0 to C of h, where h is meaning that for every point in the group, there is a uniform upper bound on the value of f. I mean, the idea is pretty simple. It just says that in this case, with a finite supported measure, you just run the walk for n steps. So this is an average over the ball of radius n. So each h is in some such balls. So this gives you the compactness by thickness. So h plus g mu is compact by thick enough with respect to the pointwise convergence, because this is the product of compact spaces, but the topology is somewhat weak, but it's fine. Topology of pointwise convergence. Okay. Okay, good. And so as a corollary, we can see that we can define x plus extremal of G mu equals extremal points in this compact convex set. And then this extremal point, and by find minimum, well, this is this somewhat generates the convex closed hull of the extremal points of the whole thing. So if we want to show that x plus h plus g mu is just one function, this is the same as saying that the extremal ones. Okay. So in the end, if we want to prove that there are no positive harmonic functions, it's the same as showing that there are no positive extremal harmonic. Okay, good. So I think it's time for break. Then we can resume 11, I don't know, 13. And then we can finish the proof of this. Okay, so now first let's finish this this proof. So we are at the point where we show that a harmonic function is in the convex hull of these extremal ones. And so if we want to show that the extremal ones, just only the trivial ones, then you have to show it. I mean, that's enough, basically. You just have to show that there are no other extremal ones. Okay. So again, so now let G be abelian. So we want to show that the extremal ones are only the constant function, and if we normalize by f of identity to be 1, then we just have this function. Okay, and the trick is to construct other functions from one function. You construct other functions that have that contradict this extremality property, basically. So okay, so let S to be the support of mu, literally the support. So this is a finite set, and we pick S some element. So we define HS of X. Yeah, so we pick H in this space, harmonic function. And then we define the following modified function, which is H of Sx times H of X. This is, again, another function on the same group. So this is a group operation, which happens to be abelian, but at the moment we haven't used it yet. So, and we recall also that H of X has to be non-zero by the same reasoning, by the maximum principle, because if the function is 0 at some point, then it has to be 0 everywhere. Okay. And so what we want to show is that this is also harmonic. The claim is that HS is also harmonic. Okay. So, well, we just have to check. So let's see. So what is HS of X? You want to check whether this is the same as the sum of HS of X t mu of t. And so let's see. So hs of x is h of sx divided by h of x. And the question is it the same as what? H of s xt divided by h of xt, I guess. Times mu t. Okay. All right. So here we have to use somehow the claim that this function is harmonic to begin with. So h is harmonic to begin with. So let's see. So really confused. So if we divide by h of s, okay, we could do that, but let's just multiply, just divide it by let's just divide it by a constant, then of course this would be true, but then this would be just divided by a constant. So let's see. Yeah, I mean this proof originally was just for the uniform measure. So maybe that's why that may create a problem. So because if mu is uniform, then we can just write 1/4 there and let's see. So the idea is indeed to find a harmonic function. And then using the fact that, okay, so okay, so let's assume that, okay, maybe this is a typo. Let's take this one. So okay, so now let's check the harmonic condition for this one. This should be easier because now what do we want? We want HS of X to be the average of HS of XT mu T. Okay. So this one is H of SX over H of S. Okay. And now let's see. So this is the sum over T of H of SXT. As we're multiplying, priori we're multiplying on the left, divided by H of S times mu T. So this one is fine because this is just harmonic like that. Okay, that's good. So we're claiming that HS is harmonic for every S. Now, I don't think we use the fact that the group is abelian yet, though, because we're multiplying on this side, right? So the other thing you'd like to notice is that let's forget about the 1/4. Let's say that the sum, let's see if this, so if you do HS HSX, so this is just, this is just H of SX times mu S. I think that's okay. This is H of X. So why is that? Let's see. So this one is, again, this is H of SX times mu S, and now here we're using the abelian condition. Right? Because this is not the definition of harmonic for the usual group, but it's the opposite. So this is by the abelian condition. This is the same as HXS mu S, which is HS. And so this is harmonic. Okay, yeah, sorry, there was just a typo here. Now, once you've done this, so what do we observe? Well, we observe that we have a bunch of harmonic functions that are here, and we're writing H as some linear combination of harmonic functions, of Yeah, of harmonic functions. And clearly, this is not good, right? This cannot be good because we already use the fact. We need to use the fact that H is extremal, right? So since H is extremal, we have to say that H equals HS for every S. And so this one, what does it tell us? Well, it tells us that H has a very, very special shape. So see, H of Sx over H of S has to be equal to H of X for every X in G and for every S in the generating set. So in particular, H of Sx equals HS times H of X. And also we are assuming, and this is true for every S in the support, but we are assuming that the support generates the whole group, right? So for every S in the semi-group generated by the support of mu, which is the group. So H is a so-called character. So H from the group to R star multiplicative group over R is a character. Is a homomorphism. And now the question is how many homomorphisms there are. Okay. So, well, let's see. Right. So H, what's about character? So if you do H of G inverse, this has to be 1. This is the character. And this, of course, is also H of G times H of G inverse. Right? So H of G and H of G inverse are inverse to each other. So this implies that H of G plus 1 over H of G, plus H plus H of G inverse, this is at least 2. Because, right, so this is the same as H of G plus 1 over H of G. So if you take a real number and you add it to its inverse, it's at least 2. Right? So now why is this a problem? So the fact is that yeah, so now if we take the sum of mu of the generator, so mu of S plus mu, so H of S. So if S is in the generators, by the way, let's yeah, okay, so here, yeah, I guess here there might be an issue with groups and elements of order 2. Let's see. So because what I want to say is if, right, so if S is different from S inverse, so what I do H of S mu S plus H of S inverse mu of S inverse, and then I sum over all S. Right? And this I can always do. And you see that, yeah, we're assuming that S is symmetric because yeah, we're assuming that the measure we start from is symmetric. So S is S inverse. And the measure mu of S is the same as mu of S inverse. We're assuming that. Okay. So what is this? Yeah, what is this? The first term, the sum of HS mu S is H is a harmonic function. So the sum of HS mu S is H of the identity, right? So H of identity is 1. And on the other hand, this one is the same, right? So this is 2. On the other hand, well, mu of S and mu of S inverse is the same, right? So this is bigger, and H of S plus H of S inverse is at least 2. So this is bigger than 2 times the sum of mu S, which is 2. Okay? So it means that every step has to be an equality. So in fact, I don't think we're using the, let's see, so far we're not using the fact that S is different from S inverse. This proof still works so far. Let's see what happens. So we need that for any S in the support, H of S, yeah, H of S plus 1 over H of S, or H of S plus H of S inverse is to be equal to 2. Right? But this is only the case if H of S is 1. So what's the upshot? Well, the upshot is that H is a character that is 1 on each generator. So, so H is identically this every S, and it's a character, so it's a homomorphism. So it's in the kernel of this one. Okay, very good. So basically, yeah. So here the only thing we're using though kind of heavily is this measure is symmetric. So for the non-symmetric case, I'm not sure there may be some trick, but it's yeah. And we use at the beginning this finiteness to prove this compactness. I think that might be relaxed somehow, but I don't know the original proof. So okay, so as an upshot, so what we have is, so the summary is that every extremal harmonic bounded function is constant. And so every one of them is. Right. So first of all, we show that every extremal bounded harmonic function is a character. And then we show that there is no, for the symmetric measures, there is no character which is harmonic. As we saw, if the measure is not symmetric, there are characters. So again, if G is abelian, mu is symmetric. The support of mu is finite and generates G. So again, the remark would be that if mu is not symmetric, then there could be harmonic characters. Non-constant characters. And again, we saw the example is if we do f of n equals q to the minus n on z. That's an example. It's a character, obviously, and it's harmonic with respect to certain measure. So it's possible, but then but this one would be not bounded. Okay, very good. So let's see, are there questions, comments? Yep.
Where did you use the support as finite?
At the very beginning, to show that this H plus is compact by Tikhanov's theorem. So we need an a priori bound on how big this function gets. Yeah, that was the only time. Well, again, this bit, I suspect that it might be, there might be a way to deal with that somehow. Yeah. Because the theorem is still true even for infinite support. Yeah, that was the only time. Okay, very good. Yeah, sorry, there was a typo in the notes at the beginning that derailed the conversation for a few minutes. Okay, very good. So now what we want to discuss is we start this discussion of this Poisson boundary. Yes, this theorem is due to Furstenberg. Sometimes people call it the Poisson-Furstenberg boundary. I think since it's too long to write, I will mostly just write Poisson. But okay, so basically we saw a discussion of harmonic functions. And the theory of the Poisson boundary has to do with the representation of such harmonic functions. So let's recall the Poisson representation formula. So the Poisson representation formula is a formula about the disk.
I have a question.
Yes.
Like in complex analysis, you have all sorts of conversions to the boundary that are not the one that we use, so like non-tangential limits.
Correct.
I was wondering if there are like other sorts of theorems, like the ones we saw, like for other like not as restrictive limits. Doesn't make that make sense.
I mean, in what sense is this restricted? This is not very restrictive.
Well, but just I guess for other types of limits. Or...
Well, I think the issue is in the general theory, as we all see, you have almost sure, you can only hope to have almost sure convergence of the walk to the boundary. So this is not restricted at all. I mean, in a way, is the most general, but you can have a more subtle, like you can have more restrictive options. Yeah, exactly. So okay, that you could, yeah, and okay, in certain situations you could say that the convergence is much better, and in principle you might want to, you could try to define another boundary that way. Yeah, but I don't think yeah, I don't think it's been done at all, but in principle it could be done. Yeah. So we'll see. Yeah. So yeah, there's two types. There's the Poisson boundary and the Martin boundary. So Poisson boundary is somewhat general and also restrictive. So it's kind of a weaker theory. And then the Martin boundary is an extremely strong theory. Like it's extremely on the opposite side. It's really hard to identify because there are too many different ways to converge to the boundary. So these are the two opposites. Okay, so let's start introducing this. So the classical Poisson representation formula tells you again that there is a duality. There is a duality between harmonic functions on the disk on the one side, and on the other side there is bounded functions on the boundary of the disk. And if we want to put a measure on this, the measure on the boundary of the disk that you're going to put is the Lebesgue measure. So L infinity as essentially bounded function. So, and there is a way to go one way and the other. And in fact, there's more than one way. So, yeah, going to complex analysis, of course, there are many ways to go this way. If I give a function on the inside, which we're gonna denote by u, and a function on the boundary, which we're gonna denote by f, well, the most natural maybe way is to take the radial limit. That would be the easiest one. So you take the radial limit, you take f of e to the I theta is the limit as r goes to 1 of u of r e to the I theta. And of course, the limit only exists almost surely, well, in fact, on a set of, the complement as capacity 0. So it exists quite often, but not everywhere. So that's one way to do this. There are other ways to do this, which are more probabilistic, and they're more closely related to what we're actually going to do, which is we can take the Brownian motion. What?
In the limit.
Say it again.
What is under the limit?
R goes to 1 minus. Yeah. Sorry. Yeah. So there is another way. Okay, again, you can take maybe other types of limits, but for instance, probabilistically, if we know how to define the Brownian motion on this manifold with negative Riemannian curvature, then what you could do is you could take the average of the function along the Brownian path. This is a much more highbrow, so it will be the expectation of what? Of the limit, sorry, as t, the time goes to infinity, of the expectation of the value of u over the Brownian path, conditioned on the fact that the Brownian path at infinity converges to psi, to e to the I theta. So this would be another way, and it's in fact it's not complete. I mean, whatever the much harder stuff is to define this Brownian motion and so forth, and prove its convergence. But it turns out that the hidden measure for this Brownian motion will have to be the Lebesgue measure, because it's just of symmetry considerations. Because the kernel that defines this Brownian motion is rotationally invariant, because the metric is rotationally invariant. So that's that. Now the other thing is how do we go the other way around? And the other way around, so this is taking a radial limit. And the other one is the famous Poisson formula. And so what is the Poisson formula? Well, it's a convolution with the Poisson kernel. Of course, if this was the Heitzmann formula, it would be the convolution with the Heitzmann kernel. And the von Taylor formula would be the convolution with the von Taylor kernel. So this doesn't say anything. What is the Poisson kernel? So the Poisson kernel is the following. Yeah, the Poisson representation formula is the following. If f is a bounded function on the boundary of the disk, then you define the following: u of r to the ei theta is 1 over 2 pi, the integral from minus pi to pi of the following convolution PR theta minus t f of e to the it dt. And then what is PR? Well, PR is this. So PR of alpha is 1 minus r squared. And then you have the sine and cosine. So it's 1 minus 1 plus r squared minus 2r cosine alpha. It's called Poisson kernel. Okay, so this is just a formula, but it turns out that from a geometric point of view, this formula is much easier to remember. If you recall that this formula is related to the geometry of the action of SL2R on the boundary of the disk. So the observation, the remark, so this is closely related to action of the group of isometries of the disk by Möbius transformations on the boundary of the disk by Möbius. So let's do this computation.
For the radial limits?
Yeah.
I guess, so you're saying like these exist, this limit exists for like,
Almost
like
surely.
almost everywhere for functions in H infinity.
Yeah.
Okay.
And you will get the same thing if you were to do a Brownian motion.
Yeah. Yeah, you get the same function here. Yeah. Yeah, exactly. Yeah. Yeah, because the Brownian motion is symmetric, so somehow even if we were here. Yeah. Okay, so what's the issue here? So how do we think about it? So recall. So think about, so let's fix origin here, and sorry. And let's pick a point A. Okay. So we want to, so we pick a point inside a disk, and we called it there R to the E to the I theta. Right. So now there is an element GA of Z in the isometries of P such that, well, I think the correct thing to do is that we want to bring GA to GA of A to 0. So we basically, the idea is if we compute this at 0, it's much easier to compute. So let's see. So if we bring this to 0 with this map GA. Now here's a question: what's the formula for such GA? It's an isometry of the unit disk that sends A to 0. Anybody remember? Can guess?
Like D minus A over 1 minus A bar.
That's exactly right. That's exactly right. Okay, now exercise number 2 is take the derivative. Now this is a very, very hard exercise for someone in math grad school, and not to mention tenured professor. So let's see. So we have, this is 1 times 1 minus A bar Z minus A bar times D minus A, I hope. That is minus 1. Let's see. And I think this term should simplify, which is 1. And then this should be minus plus minus A squared. Okay. I think that's okay. So what we find out is the norm of G prime A at Z is 1 minus A bar squared over 1 minus A bar Z squared. Okay. Now this already starts looking like a little bit like this. Okay. So if we plug in, so Z would be a point on the boundary, because you see this action is both inside, but it's also on the boundary. So if Z is e to the IT, and A is e to the R e to the IA, so the norm of GA prime of e to the IT is what? Is 1 minus R squared over, sorry, the norm of what? 1 minus A bar, so is A e to the minus I theta plus T. Right? So you see, this is extremely close. So the observation is that if you take lambda, sorry, take lambda Lebesgue measure, and you take a boundary point psi, which is e to the it. And now, if we look at the action, so if you look at the Radon-Nikodym derivative of A, G, yeah, so G A lambda, G lambda, G lambda. So the action of G on this Lebesgue measure on the circle at this point psi, well, this action is conformal, it preserves the angles. So the only thing that matters is the norm of that derivative tells you how an infinitesimal element gets expanded, right? So this G, because G preserves the circle, right? So this is precisely the norm of G A prime e to the it. And this is also, it's also this guy here, which is basically, it's exactly the Poisson kernel. It's P R of T minus theta. It just, so you see that this Poisson kernel, this seems very exotic, in fact, has a very natural interpretation in terms of the action of this group on the boundary. So let me just finish by writing the Poisson formula in a more, geometric way. Is the following. So U of A is a point inside. This is a point inside the disk. So what? This was 1 over 2 pi, right? Integral from minus pi to pi of PR T minus T F of e to the IT dt. So dt over 2 pi is the Lebesgue measure. So this is the integral over the circle of f of psi d g a lambda d lambda of psi d lambda of psi. Lambda is normal. Let's take normalized Lebesgue measures. And so in the end, this is just the following. It's the integral of f of psi with respect to this push forward measure, G A lambda. So the formula is much simpler. What are you doing? You want to find an element inside the disk. You want to find the value of the harmonic extension. You take the group element that brings this to the origin. You push forward the Lebesgue measure by this element, and you integrate against the boundary values. And that's it. So this complicated formula is indeed just has to do with the action of the group on its boundary. And so in fact, what Furstenberg did was to use this approach to generalize to any group. So that's exactly what we're going to do next. Okay, yeah, it's plenty of stuff for today. Are there any more questions?
So if you were to just, if it was that origin to start with, it's just taking the average of everything.
Yeah, exactly. So the origin is the easier case, right? Because if A is the origin, right? Then it's just taking the regular average. Yeah, exactly.
Which is harmonic by definition.
Yeah, that's right. Yeah. Yeah, so you see there's also the group of rotations is somewhat playing a role here, right? Because the stabilizer of 0 is the group of rotations, and you want your function to be invariant under this. I mean, not invariant, but somehow going to be an average over this rotations. Yeah. So otherwise, if another point you want an average with respect to the group of hyperbolic rotations, which is done by conjugating the group of rotations by this. Yeah. No, I think this is a really really cool way to interpret this because I never understood this formula before I looked at it this way. Okay, good. So I'll see you on Tuesday, but this will be online. Thank you.